Good afternoon. So after having a delicious lunch, definitely you will have try to having some sort of sleep. ठीक है, बीच में आप सो सकते हैं, कोई दिक्कत नहीं है. इसीलिए थोड़ा हमने ब्रेक छोड़ दिया कि भाई ऐसे भी थोड़ा डिले हो जाए. That is why we are just delay the session. कोई बात नहीं. Okay, thank you very much, Ratri, for giving a nice introductions for my side. Now, we had in the morning session, we have the fundamentals of corrosion and manifestation, and that is by Mr. Sunil Pancha. Then we have the session on this case studies of due to corrosion failure, that is by Sri Parisma Haribhakti. So now, a lot of things it has been involved and has been there for the academic and research institute. A lot of things has to be needed because when you have the problem, the industry has the problem. Industry has money, but don't have time to do a lot of R&D. Academia, they have mainly they want to do for research and innovations, along with that teaching. They have time for more research. So when both these two junctions is clubbed together, definitely we will have a very good gesture as far as the technical deliberation between academia and industries. So I will going to get some important testing part that is very essential as far as the material selections for any plants, pipelines, any industries in various environments. And just stick to the mainly accelerated test. There are many testings are there. Okay, but due to the time span and for technical session, I will focus only on 3 testing. So mainly I will concentrate on 3 testing part: potentiodynamic, cyclic, and EPR, electrochemical potentiokinetic reactivations. Now potentiodynamic test, for that one term is polarization. Polarization is very important. This whenever you see, whenever we debate होती है, live debate, तो बोलते कि यार आप एक कांग्रेस पार्टी में से एक अलग पार्टी में से, ठीक है, तो बोलते आप डेविएट करते हो, है ना, मुद्दे से भटकाओ मत. Like that, this is a common word we are familiar. So whenever we see the metals and alloy, they exposed to corrosion environment start corroding. Okay, there are n number of anodic reaction and n number of cathodic reaction is happening. So metal, whenever it is start dissolving, it having one equilibrium potential. That means rate of oxidations must be equal to rate of reductions. Okay, that potential called equilibrium potentials. So every metal having equilibrium potentials. But when metal is exposed to various corrosive media, fluids, open atmosphere, okay, there are n number of anodic and cathodic reactions is happening, which lead to deviate this potential from equilibrium value, and you have certain value will be changed. This deviation due to anodic reaction, it is called anodic polarizations. This deviation due to cathodic reaction, it is called cathodic polarization. Okay, so that is delta V, that is nothing but polarizations. And for this test, we are measuring the delta V, change in potential with passes of current. Okay, so when we have the test specimen, which is to be having in corrosion cell, and we pass this current, and due to which what will be the change in the potential that is to be measured, and that is being plotted as a XY axis. So this test is very important to understand corrosion potential. So when we have this data, you can find out what is the corrosion potential, at what potential metals start corroding. It estimates corrosion current, it estimates potential region of passivity. I will explain what we mean by passivity. Mainly we are using this Gabry reference 600 as equipment, and this test is designed as per the SPM G5 standard. That is mainly for making a potentiodynamic testings for various metals and other, mainly for steel, stainless steels. And you can use the various corrosive environment. Let's say if you want to plant design for sulfuric acid plant, you use sulfuric acids. If you have fluids, okay, different type, you can use that like oils as a corrosive media, and then you find out its behavior. So that is a flexibility you can have. Now, what is passivity? What I want to say? Generally, we see the carbon steel it easily get corroded. We see the carbon steel, that is low carbon or medium alloy steel, it is to be get corroded, rusted. But when we see the stainless steels, when we have titanium alloys, when you have nickel-based alloy, when you have aluminum alloys, these having excellent corrosion resistance. So when you understand its chemistry, when we understand the behavior, it's form a protective layer that is called oxide layer. So initially it starts a little bit corroding. When the film is formed, it is having a sustainable film. And this film will be act as a physical barrier between substrate and corrosive media, due to which it cannot get further corrode. That's why the stainless steel and titanium alloy have excellent corrosion resistance that is used for various applications. So when we want to understand what is the passivation behavior of various metals and alloy, when we have this plot, you can see this plot when active, passive and pitting, that is called transpassive. So when we see this with the passive domain, when there is a, you can see the horizontal portion, okay, vertical portion is there. There is a, when we start this potential, there is a change in the current, we change in the potential. When it reaches to the point when it starts reversing, when it starts reversing, the current density is going to get reduced. Then after there is continuously increasing the potential. So this potential increasing, which indicating which indicating that there is a formation of the passive layer. Okay. So once this film is formed, it prevents further corrosion. Okay. So this change in potential delta V, that will define the optimum values of passive domain. Okay. Now this film, it gets ruptured. Okay, by any means, by let's say we take the example of stainless steel. I will explain repeating it is more clear. When the stainless steels get pitted in chlorine environments. Okay. So that pit is a localized corrosion and it will damage the passive film. When start damage the passive film, the conductivity is get reduced. Okay. And then after at that point it start increasing. You can see the pitting. There is continuously increase in the current density. So that indicate the film start rupturing and localized corrosion in the patches it is to be there, and it will lead to the corrosion. Generally it forms. Okay. So this type of informations you can get by potentiodynamic test. So this is what I am talking about, active, passive and transpassive. So generally the metal dissolution rate is increased, potential is active, just like carbon steel. Okay. So when the carbon steel is there, it continues the dissolutions of metals and then start increasing the values. Passive maybe already I discussed, and transpassive there, you can see the metal dissolution rate again increase when there is a damage of the passive film. Now how we do the testing? So for any testing, it is very important selections of materials and sample preparations. This is an example we want to understand. This is my research project. We did cladding, stainless steel cladding or carbon steel, and we want to understand the three location: base metal, interface, and top of the clad. So we have to identify. So center portion, you can see there is a interface, this base metal, and it is clad. So we have to do taper grinding. When you do taper grinding, you can identify the location. Sometimes let us say for cladding technology, when you want to having 5 mm, 10 mm cladding, or any hard facing will be do, then there is a minimum requirement. Like 3 mm होना चाहिए, 5 mm होना चाहिए, 10 mm होना चाहिए. So we can prepare a step starting from 2 mm, 4 mm, 6 mm, 8 mm, and so on. And at that location, you can having a window, and then you expose this window for corrosive media, and then you can find out the corrosion rate. So as we move from bottom to top, the alloying element is changed. It's going to get at the top 100% chemistry are reaching. So when you have 100% chemistry, then excellent corrosion resistance. But somehow, due to wear and tear, that the cladding or coating get rusted, can be removed by erosion action, then I have 2 to 3 mm, let us say it is to be there. But 2 to 3 mm cladding is there, whether it is sufficient or not, that is again given by various specification, ASTM or ASME standard. Different standard specification is given, section 8, section 9 for welding. So depend upon that, you have minimum thickness you have to maintain. Okay. So at that location you have to selection. That is why for testing, selection of location and what depth you want to understand corrosion behavior is very, very important one. And when you want to connect this connection with the help of, you can see it is connect with a cell. It is called corrosion cell, and corrosion cell is connect with the potential state. The potential state, in which there is 3 electrode. One that is for reference electrode, that is for caliber electrode. One counter electrode, that is of graphite, and one working electrode, that is for test specimen. So we are supplying the current by means of counter electrode and changing potential and measuring with change in the current, and you can plot this curve current density versus potential. Okay, that we are measuring, and finally when you get this plot, then you go for analysis. So this is the software, I just steps you have to follow, you have to give the data. When you want to run this software, there is very important, what are the parameters you have to insert. There is initial and final voltage. Generally for carbon steel, let us say if you want to understand the corrosion behavior of carbon steel, you can go minus 0.5 to 0.5 volt for scaling the range. But when you put stainless steel, so titanium based alloy or inconel based alloy, where it passivated after a prolonged period of time. So that is why you have to give more exposure time and more potential value. So range it is to be 1.2, 1.7 you can go up to. Now when we see the conductivity time and initial delay, when you have the test specimen, when you handling the test specimen, what happens? Some chemical will be there on the fingerprints, will be there, some glues are there. So that will lead to change in the chemistry of the surface, and definitely for corrosion, when the chemistry is changed, the corrosion rate will be changed, corrosion behavior will be changed. So it will, so when you expose, this time is given to clean the specimen, sample area 5 mm by 5 mm, yeah 1 mm, 1 centimeter by 1 centimeter you can put, density and equivalent depend upon the alloys. Now how you can get which type of plot you are getting. So this is plot you are getting, this is for stainless steel. Generally you can see the grade stainless steel, थोड़ा clear नहीं हुआ इसमें, but this is for 309 grade LNT grade stainless steel plot. Here you can see when it start passivating, you can see the formation of passive layer is very, very thin. But when we go for this 430, there is ferritic stainless steel plot, then the passive domain is to be high. Just I want to make sure that when you change the alloy for the same corrosion media, the behavior of that alloy is changed. Okay. So for sulfuric acid, you can go for austenitic stainless steel. And for nitric acid, you go for ferritic stainless steel. Why? Because in that environment, the behavior will be different. It is to be better. So you can see this is cladded. Okay, and next one, that is okay. So this is tuffled extrafloration. What is tuffled extrafloration? So when you have this plot X and Y, we want to find out E-core, I-core, and corrosion rate. That is to find out by using, you have to select the linear portion of the core and you can extrapolate this core. Whenever it intersect, the intersection point on y-axis it is for equal value and x-axis is equal to I-core value. And from that you have the slope beta and beta c. So this bottom curve you are observing, this bottom curve it is called cathodically polarized. That means sample became cathode and change in the potential you are measuring. Then after it is anodically polarized when sample became anode. Now when we talk about the coated sample, generally various coating industries are there, phosphating, anodizing, or I am just talking about the conductivity, because when we are having non-conductive film, then it is not applicable. For this is conductivity. Now when we can polarize first cathodically, then anodically. We can do anodic polarized first and then cathodic polarized. But when we are doing the reverse manner, because we want to understand the behavior of the coating when it is behave cathode and anode. So once you have cathodic behavior, you have the data. When it start anodic behavior, it start dissolution, there is change in the potential. The film get rupture, the coating get rupture, remove हो जाएगा. Okay, and then you have the data. अगर आपने पहले anodically polarize कर दिया है, तो initially your film get rupture, उसके बाद जो behavior मिलेगा, that is only for your cathodic behavior. अब वो film का नहीं होगा, वो किसका होगा? आपका base metal का होगा. That is why this design, this test first cathodically polarized, then anodically polarized. Now this is just, I want to say this the data of how this welding speed, which vary of 309L on L, this is for L base metal, interface and clad. Okay, so you can see the base metal, this is a blue one, 539 MPy. For interface 439 and for clad 156. That means at three different locations, when you start with base metal corrosion rate very high, it is goes on interface, there is an increase in alloy elements, the corrosion rate decrease. When you go for top of the clad, the corrosion rate further decrease. That is called 156. So how this way you can identify at what level which type of behavior you are getting. Next is cyclic polarization. Cyclic, generally we see the pitting generally in the initial fundamental of pitting study which is to be there. Pits, very dangerous corrosion, localized corrosion. But we generally what happen, pitting suddenly occur and lead to the corrosion. But when we go for selections of materials, then we conduct the test, it is better idea to understand how the metal is behave under pitting when it is exposed to that environment. So for that, this is the just information you can able to find out. Cyclic polarization test, you can get E-core, I-core, corrosion rate plus repassivation potential. What is repassivation potential? So we can say it is an extension of potentiodynamic test. And this test is performed as per ASTM G61 standard. And you can use for, this is for nickel, cobalt based, and 6% FeCl. It is very, very aggressive environment. We can use NaCl. Generally 3.5% NaCl solution is used. But FeCl is very, very aggressive. If certain alloys which is passed, definitely will pass in certain environment. So sample preparation just like potentiodynamics, similar, I am not going to be there. This is the software you have to run, you have to feed the data. These are parameters. Initial voltage and final voltage. Generally, the initial and final voltage is nearby range. There is a forward scale and reverse scale. I will explore this forward and reverse scale. Apex value, that is the value of maximum current which is to be reached from which start reversing this curve. I will explain how it is there. And other thing, sample inner density. Now when you connect similar setup will be used. Now you can see the plot. First, when you see that is a potentiodynamic scan. Just हमने पहले देखा था similar. Actually pointer we are not, screen is there, so I am not able to just catch this. So, but you can see the initially cathodically polarized, then anodically polarized. Okay, that is just like a potentiodynamic. But it reaches to value, certain value, and start reversing. When it start reversing that value, that is called apex current. That is 1000 ampere, milliampere we have kept. And when it start reversing, in reverse scan, it is first anodically polarized and then it is cathodically polarized. Now, how to analyze the data? So, whenever you have the loop is formed, definitely it will intersect, it will cut each other at certain location. That location, it's called repassivation potential. Just like in when they start with the potential dynamic forward scale, it reach to certain value and start pits formation. That's fine. But it is okay. Pits occur. You know, this is a value where pits start. But we want to understand how the pit gets repaired during service condition. Whether this alloy is sustainable to reduce the pitting behavior. So whether it intercepts the point called repassivation potential, and this repassivation potential is very, very important, which give interpretations of analysis. So this analysis will be given by two loops, one called negative hysteresis, another is called positive hysteresis. Negative hysteresis here, when reverse scan current density is less than forward current density, that is ERP, that is interception point, ERP, repassivation point is greater than equal. Okay. So whenever in potential dynamics scan, this is the value, center you will get the equal value, and whenever intercept, that is called repassivation potential. Now the ERP on the passive domain side, okay, when it is on passive domain side, it is in having higher value than equal value. In that sense, the damage passively will be repaired and it will prevent further corrosion. तो ये केस में आप बोल सकते हैं फिटिंग में सैंपल पास है आपका. लेकिन अगर वो रिवर्स होता है, when it is intercept on lower side in active domain, when ERP is less than equal, that is the repassivation point is less than, that is just like uniform corrosion. जो number of bits हमने देखा SS का during the presentation by Mr. Hire, the pits, the stainless steel get number of pits in chlorine environments. So when the SS get pitted at number of locations in chlorine environment, you will get positive stresses. That is quick weight failure. This is just give the one data, that is you can see the behavior. This is again my research data. You can see we have find out the two values, one for L and LMP. That is called, we did the development of 309 L graded weld overlays on low alloy steels, L grade and LMP grade. You can see the data, the LMP, the Naga medicine. Until now, as far as the metal industries and manufacturing of stainless steels or fabrication industry, you know, the Naga mainly aided in steel to improve internal granular corrosion resistance, IGC. Okay, in the morning we have IGC fundamental, CR20 precipitations. Okay, so to do the Naga, there is no formation of CR20 C6 precipitation, and that is why it having resistance where IGC is improved. But in my research work, we find out that when we add Naga, there is also improvement of pitting resistance. So until now there is no such information was available. This now will also improve the pitting behavior.